Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
Hey, Kirk. Once again, we started chatting about stuff, and you mentioned you got a paper, and I know it's a pet peeve, both of ours, that we think, why are they trying to take a HALT test, which by its nature is an exploratory series of step stress applications to find what fails? Where's the margins for these various things? How can we uncover what we don't know? And they want to take that experiment, that set of tests or stresses we apply to something, and then model. I think this paper was on vibration and saying, we're going to be able to predict fatigue damage accumulation on something.
Yeah, you're right. And compare between two different machines, like an ED shaker and a repetitive shock HALT vibration is what it's typically called. Vibrations, multi-axis, and trying to build scalars of saying, okay, this one will create a lot more fatigue damage than this one, or this in this spectrum, you've got more cycles, and you kind of develop an SN curve. And as I say, that's you can do these kinds of things for finite elements, for a particular, BGA or something like that. The ball grid strains and stresses on that.
But it would be on like a particular style of ball grid array with certain number of pins, certain size, certain plate thickness, certain size of ASIC in it, on a particular wherever it's mounted. Could be in a socket, or it could be mounted right on the board. But then what's the size of the board? What are all the dimensions and sizes of that? And very, very quickly, I mean, I've run into people that, like for vibration, like crack fatigue, and they're using tensile bars. The only product that's a tensile bar is a tensile bar.
I know. They use a very simple device and try to extrapolate to very complex, interactive, resonances of the system. When you put a simple PC chassis with its motherboard and power supply, there's 1,000 different resonance frequencies in there, and you're stimulating each one at a different rate. Also, talking about this with an individual, I said, temperature makes a big difference on the frequency vibration of materials, and
at a material level,
at a material level, if it's warm, it's going to be more flexible. Generally, plastics, FR4, they're going to flex at a different frequency. They're going to have it's going to shift their natural resonance frequency.
Oh, we don't worry about that. We keep that constant.
I know, and I know it's theoretical. Well, we'll assume this. We'll hold this constant, even though it's not. We can't do that.
Mother Nature doesn't care what your assumptions
That's right. There is no sine vibration in Mother Nature. Very rarely. I mean, you might have it on an engine, aircraft engine, or something like that.
I was on a road that had it. It was, I think, it's where it's waffle bordered or whatever.
Right. Yeah. Where everybody all their cars get into this resonance that makes a waffle, a ridges.
Set of ridges about 6 inches apart.
Right, exactly.
Miles. Yeah, that's
and
it
just keeps accelerating itself by every car getting into that resonance.
It going, yeah. But the idea, though, it's not just vibration, which is in its nature very complicated to model.
Very complicated, right.
I also heard this question the other day, and it was kind of the idea by asking, when you mentioned this, the one you're talking about, the same concept applies, where she was working in like a PhD program, and they're working on these system models that are just amazingly detailed.
Right.
And I said, well, do you take into account temperature? Do you take into account this and that? And we have about 87 different inputs to this model for this circuit board or whatever it was. I said, does anybody that could use that in real life know how to get 87 inputs?
I know. How to measure all those 87 things. That's my point, is also, okay, you measure vibration. on one part of the circuit board, but it's very different on another part of the chassis. I mean, they're all resonating at their own,
They
especially
all do
when
their
you,
own thing. Yeah.
yeah,
And at the end of the day, what we're really looking for is, we can go into halt and we can find the vibrate, we can see the vibration sometimes when it's bad enough.
yeah,
But if you didn't mount it the same way you're planning on mounting it in your system,
you could get
you
irrelevant
could get all kinds of erroneous
right,
things or different things that you're
exactly.
rechasing. And so some of it is you got to run the experiments well and do the testing well and be aware of all those variables. Yet what I told this one researcher was, what is the end goal? What are you trying to actually do with these models?
Exactly.
And they're trying
Exactly.
to improve the accuracy of the system model for reliability. And it's like, is that really what we need? Because it gives you an estimate and it may be more accurate, but does it lead to anybody making decisions of which component to improve or where do we focus or, the practical stuff? How about we just do a simple series model and ask each of the team members, the lead of electrical and the lead of software and so on, what is the reliability performance of your element of this? Right? And then all you have to do is look at which one's the weakest link, the least reliable, and say, all right, Bill, you got to go fix that, improve the reliability. And it might be improving the accuracy of the estimate, might have been just a guess, or they improve their product so it's more robust. And
Well,
we
right.
can
It
we
depends on
can
what stage of design it is in.
right. The idea though, Kirk, is that you do that right from the start. And right at the start, it's just a guess. But
Well,
it
right.
starts the conversation to pay attention to reliability, but we all don't need to pay attention to it. Only the areas that are causing the system's predominant failures. And then
Right.
as that evolves, our knowledge evolves. Now it might be those connectors we talked about in the last episode. We got to
Right.
fix the connectors. But instead of everybody trying to improve reliability, it is focus energy and resources in the areas that really need to be improved. And it's a strategy to say, and you've heard it from Carl and Kirk or Carl and Chris, is that let's focus on the vital few. What are the ones that matter? And Halt's a great tool if you don't know where the failures are or what you need to work on. It's a way of identifying those things, and it
Well,
helps you identify them.
nobody designs anything expecting or having knowledge of it being unreliable or, you know,
Oh, yeah, you haven't worked with a military
well,
contractor lately, have you?
you wrote an excellent article and put it on LinkedIn, and I definitely agree with it that there is, and I even commented, I don't know,
Yeah, I saw
that
that. Yeah, thanks.
there are those industries that have been oriented to making a profit off of service and spares, and that makes a very big conflict in making a reliable product. But in commercial industries, nobody's building the designers generally that have competition in the market aren't going to build something that says, well, I know this is going to fail in 3 years, but by that time they'll buy another one.
We'll
I
buy
don't
another one
I
or there'll
don't
be no.
believe I don't believe anybody really knows that there's, except for the battery in an iPhone, that any of those components are actually going to wear out and say less than 15 years,
Yeah,
I
and
can't
I mean, all
imagine it.
kinds of industries have gotten better and better. It used to
Right,
be,
right.
you would buy stuff more often because they just weren't robust to
Well, and right,
enough.
they didn't have uh, uh, as we have built electronics over the many decades, we've certainly got better, and also it's become more compact, and there's less, uh, you know,
Things to move around. Yeah.
variation. Right. Look at it. We were talking about cabling, and I just think, well, what kind of cabling is in an iPhone?
Yeah. I remember one time
Not really cabling.
I was working with a company, not with Apple, but with another company. It was a very tight space. And they had an optical channel and it didn't have anything in it. It was just an open space that they could
Hmm.
send a signal from one side of the device to the other side
Hmm. Hmm.
at a good enough frequency for what it needed to do to
Hmm.
communicate to the other side. And when I said, why don't you just put a wire across there? Is we don't have space for a wire, but you can see the light shining through this little gap.
Yeah, and it doesn't take much light, depending on, but they do have, actually, I do think about an iPhone. They do have little tiny connectors in there.
Mm-hmm.
Really tiny.
Yeah, no, it's
You got
amazing
to
what they
get
can invent.
tweezers.
Yeah, it's amazing what you can create when you really set your mind to it. And but it's
But getting back to modeling and vibration and the damage,
well,
the
all of those
vibration,
things
all
is
those things, to me, they're all, maybe they can, to some extent, well, I assume CAD systems and a lot of multi-physics uh, capabilities in the CAD now, and being able to do simulated vibration
oh
on
yeah,
a
yeah.
mechanical system. So that to me is probably the most valid approach when you're in the design phase.
No, but yeah,
Yeah.
no, Kirk, I think it's even simpler than that. Make a prototype and drop it. If you're worried about
Well,
impact from drop, make a prototype and drop
of
it.
course, Fred. Once you get real hardware is when the real knowledge starts for
You
me.
can make real hardware with it doesn't have to be with your molded parts. I mean, you would want to do that
Well, you have to be
eventually,
careful
but
about that
I know you have to be
because
careful about it. But if I'm
molded parts
curious,
are different plastic that may have a
but
very
if I'm
different.
worried about harmonics or I'm worried about this or that or the other thing,
Right.
I can
Okay.
keep it simple.
Right.
Learn what you need to know and don't spend 3 months doing a PhD level study of it. Is my
Right.
point is that yeah, we've got finite element, and it's a great tool. Yeah, you got to know what you're doing. We can test it, and we can make mock-ups and protos, and
Right.
we can test it. We got to know what you're doing, but we don't need to start off by saying we're going to do this, breakthrough technology, and we have to invent a way to analyze it, or build off of some obscure modeling system. Like, what can we do that will help us answer the question? And yeah, sometimes you need to do the exotic stuff. But oftentimes what I see is if the real goal is to increase the ability for us to understand how it fails and when it fails, or how do we design so that we build a robust system,
Right.
oftentimes there is a simpler way. And I find very educated people that love the, oh, I'll get a staff of 28 engineers and we'll work on it for 3 years. Now, hold on,
Right.
Bill. We got to ship this next month.
Right.
You
Right.
know, what can we do now?
Right. No, I think your first suggestion of build a prototype and test it, physically do something to it, and that's what, I'm saying. That's my main philosophy. 80% of the value. Get your hands on an actual product and actually start putting some stress to it. Do
Yeah,
what do what's going to induce fatigue damage that's going to happen. Do it in a controlled environment where you can observe and monitor the levels of stress until it does fail.
yeah,
More margin is great. The more margin, the better.
yeah,
The potential
yeah.
for reliability. The more margin you have, the high stress margin, the higher potential. That includes vibration, voltage, frequency, variations, all that.
Hmm.
So it's just a real simple idea. The only time you really have to estimate, and CAD really does a great job in multi-physics models, is before you actually have the physical hardware. But all of that is just, as they say, all models are wrong, some are useful.
Hmm.
Uh,
But it's keep it in mind. It's not just because I have this model, I need to use it. Is will it answer the question I'm trying to answer?
right.
And sometimes your engineering judgment is just fine,
Right.
you know?
Right. You don't have
And
to always say this FR4 material the right material to use for a sub circuit board.
yeah,
Should I use something different? No, that's probably pretty reliable through hole technology, surface mount, all that. You don't need to re-question everything.
now if you're in high frequency stuff and you're moving into that, then do the research. Some circuit boards handle high frequencies way differently than FR4. So
Right, right,
it's
right. You have to have that signal knowledge about signal integrity and transmission lines, and of course, I wrote a paper about the issues of signal integrity and
mhm,
hardware variation, and we'll post some variation on that with Xendo at some point here.
yeah.
But it's just a matter of there's so many factors, and it is going to be something that AI is going to help us a lot more with in the future, I think,
Well,
because there's
yeah,
so many
Carl and I were
factors.
just talking about it. You might want to listen to that one a little bit,
Yeah.
on FMEAs. But the idea is in practice,
Mm-hmm.
if you keep it simple, it helps if nothing else, it helps clarify what question you're trying to answer, what problem you're trying to understand. And you need that before you go find a solution. And part of the problem I get with, the researchers they're trying to get published at conferences, and I don't know how many I sat through where it's somebody would stand up and say, "Is this practical in the real world?" And they'll go, "No, not really, but it was interesting research." And half the room gets up and leaves.
Yeah, exactly. That's half of academic articles are maybe not 70% or more. I don't see practical, application in the industry. Some of them are very, like lithium ion battery research by Cal's is very practical on the fact that they wear out. It's
But
very
the
practical.
idea though, Kirk, is that, like if there's usually more than one way to solve a problem. And I find folks that have a hammer will pick that solution. They'll just hit it with a hammer and get some answer out of it, which is actually pretty simple. But if that hammer actually means that it's 2 weeks and it's going to take 3 gigawatts of computer power to run the simulation,
right?
Well, do you really need that? And I think that question gets missed sometimes because I'm really familiar with, XYZ tools, so I'll always use that because I can understand it, I can interpret it, I can do all this other stuff. Whereas the problem I run into is that then they then miss what are the real issues that you need to be dealing with. It might not be getting another 1/10% accuracy on XYZ problem. It's, oh, hey, it's failing here, here, and here. We got to go solve those, and
well, that's right. You got to find it's failing. That's nobody when they do the CAD and design, they don't say, well, this is going to fail probably,
well, there's
run
some.
it
There's,
any.
I've run into good mechanical engineers who look
Okay.
at stress concentrations and stuff, and they go, yeah, that's not good. We need to fix that.
Okay. During the development,
During
before
the
they put it
design,
in.
early design
Okay.
stuff, yeah.
Early design. That's fine. Okay. That's great. But I think that, again, the complexity of most systems, if you're building something more than a brick power supply,
Well, which is
a wall
complicated
wart,
enough.
yeah. But, as you build up into a system and a card cage it's just way too complex with the vibration to say that, how much fatigue damage you're going to create with this spectrum and how it's going to be what it means and the scalar of fatigue damage. I just don't, to me, again, you got to touch the product. I feel like a lot of this modeling and everything is because people don't want to actually go down to the lab, put the product in a chamber and actually monitor inside, plug in the cables and put some stress to it.
Yeah.
At first, and keep it simple. Like you say, keep it simple. One stress at a time.
Yeah.
HALT is not combined stresses. Please.
Not
Not until
you can't find
the
anything
last
else.
thing.
Yeah.
Yeah, the very last thing.
I wanted to ask you is that, talk about prototypes and stuff. I remember we used to create a system mock-up basically, or prototype of a system, but we would always get one or two of the models that had a clear outer surface.
Yeah.
And then we'd put a camera on it,
Yeah.
and watch it.
Right.
And oftentimes just watching that circuit board or that cable flopping around or whatever was all we needed. We didn't have to wait for failure.
You use a strobe? I've done that too. You can
Oh,
see
no, that's a good idea. I
strobe
have never
light
used
is you
that.
can actually make it look. You can see the modes of bending a
Yeah.
lot of times in the board.
Well, I had one of them where this guy was convinced that doing an edge connector on one end of a long circuit board and
Yeah.
standing it perpendicular to the mass of the inkjet printer going back and forth.
Uh-huh.
And the printers in that family of ones, that had all
Yeah,
the
it was
ink in it and
flying.
everything. It was moving back very quick, and it was rocking and shaking the whole system. And then they said, well, to get this a little smaller and do this, and we have to do this connector on the edge of the circuit board and just put it vertical here. And I says, is there anything holding it anywhere else? No, it's too technically difficult, blah, blah, blah. And so I had the clear skins and we put a camera on it.
Yep.
Started it printing something, and like 20 seconds later, it stopped. And it wasn't like it was done printing. It was just the computer stopped. It failed. And we went back and looked at the camera, and it was a high-speed camera that we were using.
Yeah.
which was
Yeah.
brand new to the lab. We thought this, we
Right.
got to play with this. And you could see a component that just detached and then was spiraling away and hit the outside chassis and bounced down.
Escapee.
Yeah, I'm free.
I'm
I'm making a
free.
run for it, guys. Follow me. And then you could see it just, and so we took
Yeah.
that clip.
Yeah.
I didn't say anything with the main person that was saying that's the way it had to be. There wasn't a possibility to do anything
Right.
else. I showed him that clip, didn't say a word, and I left.
Yeah.
And the next day, that circuit board had 3 more connection points.
Yeah, it's sometimes it's that's a fairly easy fix is just another mounting uh hole or
Well, according to
something.
him that day prior, it was impossible. The stacked
Yeah,
up and there was
exactly.
assembly
Yeah, go
problems and the
away. Yeah,
cost
this is
and
good enough. Right. This is good enough. Oh
yeah.
yeah, let me show you that's not.
Well, we didn't honestly know whether it was going to be a problem or not. We suspected it was going to be vibrate. It would pick up some
Right. But
waveform of some sort.
you found out from the real hardware in a real vibration test with a real
Oh, it
camera.
wasn't even a vibration test. It was just printing like it's supposed to do.
Oh,
It
that's
was
right. It was
room
just you.
temperature functional
Right.
operating.
Yeah. I
Now,
haven't.
sometimes you keep it really, really simple. I mean, I
Yeah.
could have gone off and said, oh, here, given the moments and modeled that and then find an element and everything else.
Yeah.
Um, but I just need to look at it,
Yeah.
and
It's funny that I have an HP printer on my desk here, and suddenly
mhm,
it'll start. My wife or somebody will uh,
send a print job to
yeah,
it.
and then suddenly I'm sitting there shaking and my monitor's shaking and
Yeah.
everything on the desk is shaking. And I'm thinking, did anybody think about that? That the monitor is going to shake when you have a printer on a nice, on a normal kind of
That's user
flexible
error.
disk?
That's just user
Yeah,
error.
that's right. How much do they expect this monitor to vibrate? Not much generally, but
Not much, but sometimes it's enough to walk other things off your desk, including the printer.
yeah, exactly.
It really can. And I know they talked at one time they talked about putting dampeners on the feet of the printer, and then it would add like $30 to the printer. And they're like, no, we're not doing that.
Yeah, that's right. It's go have the customer put it on, or
Yeah.
build his own. But no, I can see modeling vibration, shock for things like the rockets taking air,
Oh,
things
acoustic
into
shock is
like
something they
yeah,
take advantage of
yeah.
too. It's
There's a lot
amazing.
of things that you really can't, you can't put in I'm sure those satellites or uh before they're launched, or certainly they go through vibration tests. They do a lot at the JPL. I've seen their equipment and
Yeah.
even shaker tables, vacuum equipment. They've had to, you
Well,
know,
they even put people into the equivalent of the forces and the stresses that you see
right, the
during
G
liftoff.
forces, right.
Yeah, and say, all
Yeah.
right, well, that one passed out. You're out of the program.
Yeah.
But
Yeah.
it's there's a lot you can do about it. But the idea is that
But the
if
bottom
there's a
line,
simpler solution, use that.
yeah, the simple solution is put it in a chamber and shake it, or an ED shaker, any kind of thing to a point
Oh,
where
give it
it
to a teenage,
fails.
give it to one of our teenage kids.
Yeah, until till the point that it fails, and
Yeah,
monitor that level of failure and compare that with the other 5 samples if you can. Hopefully, at
yeah,
least 3.
yeah. No, I know what you mean.
That's my take, and
All
all
right,
the
yeah,
calculations don't provide any more uh, detail or specific than a test. I mean, that's the bottom line. The proof
yeah.
is in the pudding.
Yeah, no, I'll leave it at that. It's like, if you're listening to this, hopefully we didn't, set you off to cancel your subscription to our, or, listening to the show. But the idea is, you know, how do you pick the right tool or approach to solve a problem or understand an issue or find failures or whatever do you tend to have a range of options depending on what the particular issue is and how precise or important it is? Or do you just use the same old all the time and work, and that may work. There's nothing wrong with it if it's working for you. But the idea is that if you can keep it simple, it has so many advantages from cost and time and trying to explain it to anybody else and all that stuff. And yeah, there's value in the more complex and nuanced stuff at certain times in certain places. It's not the norm, in my opinion. But if you've got a different opinion on that, you've been listening to this and yelling at your computers, or hopefully not driving, get upset with us. But let us know. What do you think? What's the appropriate way to approach, vibration and fatigue damage, and modeling it in systems, or system modeling, and just understanding the reliability model and what's the effect that has? Let us know. How do you deal with all this stuff? Head over to accendoreliability.com/go/SOR. There's a couple of ways to get in touch with us. Kirk and I and the other hosts are available through LinkedIn and our About pages. So give us a shake. Ha!
You're coming up with all kinds. Yeah,
I apologize.
Right.
I have to go outside now. Step away from the microphone.
Yeah. No, that's right. Great, Fred. We'll talk again.
Yeah. Thanks, Kirk.
Okay. Bye.
Everyone. Cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.